Good afternoon, everyone. Today, I'm very glad to introduce our new concept, Microscopic Dynamical Entropy, MD, which explains the second law in the pure Hamiltonian dynamics. Let's briefly review the problem. Classical statistical mechanics aims to explain thermodynamics from underlying Hamiltonian dynamics. But the problem is that in thermodynamics, when we say entropy, we mean thermal entropy, which increases in cycles. But when we look at microscopic world, we say entropy, we mean Gibbs entropy, which conserves under Hamiltonian dynamics. This is usually referred to irreversibility problem. And people solve this problem by changing the dynamics. For example, by inserting cross-graining between Hamiltonian evolutions. Of course, this can make Gibbs entropy increase, but this still does not make them match quantitatively. And look at these two entropies. They are totally different. Gibbs entropy is sensitive to distribution, the whole distribution. However, thermal entropy, it does not care about the inside of the heat bath, and it's totally determined by its energy. So they are fundamentally different, and the Gibbs entropy is not the micro entropy correspond to thermal entropy. And so what is it? It's the MD that has the micro thermal entropy. We study couple of Hamiltonian system with Y much larger, so it is the bath. And the MD is defined as the Gibbs entropy of X, it has the inverse temperature, Ex as average energy of X, and this is the background term. And the core result is that you can obtain, it naturally aligns with thermal entropy, and the core result is that you can obtain MD if you replace the real distribution by this cross-grain distribution. The point that we describe the internal of bath by this conditional probability, and if you replace this conditional probability with a uniform distribution, then the Gibbs entropy becomes MD. We don't change the dynamics. The dynamics are pure Hamiltonian. We say that if you throw away the internal information in the bath system, then the Gibbs entropy becomes thermal entropy. So the so-called total entropy in classical thermodynamics or stochastic thermodynamics is actually the entropy change inside the bath system. Very roughly speaking, thermal entropy equals Gibbs entropy of a uniform bath. And we can prove that if the dynamics of X is autonomous, then MD increase monotonically. This is of course true if X satisfy a Fock-Punt equation. And we study the Zwanzig model and calculate the MD. It indeed behaves as a micro entropy. And here, even when the total system is finite, not very large, and even X is not strictly autonomous, MD still increases and shows irreversibility behavior. So we don't need a very large system to have irreversibility. So the conclusion is that, roughly speaking, thermal entropy equals Gibbs entropy for uniform bath. And we do not need to change the dynamics. And so this is a natural solution to the echo paradox. And MD itself is a fundamental microscopic entropy. And it can be applied to finite systems and more general systems to describe irreversibility. Thank you.